Okay, so this talk has been curated out of um, quite a lot of work that we did on 2D materials, plus a roadmap paper I had written last year for nanoletters. So you can read a lot about that from that. The title of that paper is precisely the same. So if you want to download that paper, you can you have this title, search it, you will find that nanoletters paper, which I authored. So here is the outline. I'll talk about in the beginning, give you a gist of what 2D materials are, its properties, applications, also where the world is. Then I will try to establish a roadmap for 2D materials technology leading the future and also enabling heterogeneous integration. And then I'll dig into the science, technology, and reliability challenges as far as the 2D materials are concerned, and within which my focus is going to be on, as far as the science is concerned, I'll talk about contacts and the quantum chemistry of contacts, how we engineer contacts. Then I'll talk about the technology in terms of demonstrating N-type, P-type transistors. Demonstrating P-channel operation is a challenge in its own, and also talk about other technology and reliability concerns. So fundamentally in 2D materials technology community, the major concerns are how to make contacts. I mean the material has fantastic properties, but if you don't make a good contact, you don't exploit those properties. So that was one problem, and we have worked on graphene and many other 2D materials, and I'll talk about pretty much all of them. The other challenge was, for example, in case of 2D semiconductors, was how to make N-type and P-type transistors. And in fact, many of you would have noticed a general notion in literature or in the community that 2D TMDs are fundamentally N-type, and that's a wrong notion. So we broke that notion. We built this technology. So today we have a process which is wafer scale. We demonstrated on CVD as well, and also we worked a lot on several reliability concerns. Without addressing reliability, you cannot convert a technology into something which industry eventually is going to adopt, for which you need to understand if there are possible reliability concerns. And sometimes what happens is that with any new material, you start exploring newer concerns compared to what the other material or technologies would be offering, and that's what I'll talk about towards the end. So what are 2D materials? 2D materials fundamentally are materials which exist thermodynamically stable in a two-dimensional plane. They in principle don't have a third dimension. Some materials may have additional layers, so fundamentally they should be monolayer, but in principle some materials are monolayer, some materials are basically would have a few layers or maybe a few atoms forming that monolayer. Now they fall into different categories. Exenes are basically graphene and phosphorine and families of this kind. These are all monolayer 2D materials. Then there are transition metal dichalcogonides. So these are basically chalcogons. Chalcogons are sulfur, seleniums. Transition metals are moly, tungsten, right? So these are basically chalcogons of transition metal. Then you have insulators such as hexagonal boron nitride. And then you have other families as well, which a lot of, I would say, chemists explore: hydrogenated and fluorinated exenes, SMCs, and so on. Now, so far, these materials have been demonstrated, for applications in electronics, optoelectronics, sensing, even now quantum and neuromorphic. Over 700 2D materials have been predicted to be stable, right? And there are different market reports depending on what will be the market size by 2025 or 2030. It all depends on how fast industry adopts it. I'll talk about some of the industry adoption a little later. So I have divided this talk in the following way. You will see both graphene and TMDs going side by side. So I'll talk about graphene, then I'll talk about TMDs. If I'm talking about contacts, I'll talk about graphene, then I'll talk about TMD. If I'm talking about transistors, I'll talk about graphene, then I'll talk about TMDs, right? I'll try to basically put everything in a more structured fashion. So as far as graphene is concerned, it's basically carbon atoms which are hexagonally arranged. It's a one atom thick sheet where you have these carbon atoms arranged in this hexagonal fashion, where each carbon atom bonds with 3 other carbon atoms, right? And you have basically this in-plane sp2 hybridization forming this sigma bond and out-plane pi bond. This in-plane sigma bond is responsible for the strength, thermal conductivity. Out-plane pi bond is responsible for its electrical or superior electrical properties. Right? If you compare graphene with other materials, and as you know that, for example, mobility is one of the parameters which defines how good a semiconductor or a material would be in terms of its transport properties. So mobility wise, graphene is superior to almost all other materials. If you look into the saturation velocity or the carrier velocity, also graphene supersedes many other compound semiconductors and certainly silicon. And if you compare other parameters compared to say copper, graphene supersedes properties such as maximum current density, melting point, tensile strength, and so on, right? And this is the reason why graphene has been projected for so long being a wonder material. It's a different matter that people are still trying to adopt this in an industrial environment, in a large scale environment, but these are the promises. Now another aspect of graphene is that theoretically it was shown that you can actually build terahertz kind of devices with graphene, and that was practically not possible because the other materials could not push the boundaries to terahertz. Now if you talk about 2D semiconductors basically, for example, if you say TMDs, so in this case, say suppose you have a transition metal, these are chalcogons, right? And depending on the phase in which the transition metal and the chalcogons are arranged, they can be 2H phase or 1T phase or trigonal prismatic phase or octahedral arrangement. Depending on this, you get different characteristics. So 2H phase is the most common phase which leads to a semiconducting property or semiconducting phase, and 1T phase is also possible, which basically results into a metallic state of the material, right? Now if you compare the TMDs with silicon and other things, what you notice is that if you compare the TMD nanosheet with silicon nanosheet, right, the mobilities are far more superior. Now I am talking about nanosheet because, for example, if you have to build a next generation transistor, right, which is say better than FinFETs, you compare with FinFETs, right, you compare with nanosheets, right? So in FinFETs or in nanosheet transistors, what would be the typical silicon film thickness? Not more than 5 nanometers. So when we compare the mobility of MOS2, which is certainly less than 5 nanometers, versus a 5 nanometer or 10 nanometer thin sheet of silicon, you find that the mobilities are far more superior. Now on top of that, the TMDs or the 2D materials also offer you a very wide spectral range, right? So what is the advantage of this wide spectral range? You can basically use it for various optoelectronic applications. Now this was a limiting factor in bulk semiconductors, that you have possibly those limited band gaps available, so you have to tune or play around those band gap values. But with these 2D materials, you have depending on which material you choose, you have the entire range available from the infrared all the way to ultraviolet. So then you can use it for a range of optoelectronic applications with varying wavelengths required. On top of that, 2D materials are also highly flexible.
One small question. Can we also tune the band gap within the same material, like if it is MOS?
Yeah.
Is it possible to
Yes.
do something to tune the band gap?
Not in the same material, but people have shown certain gating techniques to tune the band gap, or heterostructures to basically play with the band gap or this optical band. So that possibility exists. You have more playground, better playground compared to what the bulk semiconductors offer. So 2D materials are also highly flexible. So you can think of building flexible electronics. They're also sensitive to a lot of volatile organic compounds. So you can use that to build sensors. In fact, in 2D materials, you can also design the sensitivity for a certain volatile organic compound, right? Completely physics based. So that's added advantage. Lightweight, so you can build lightweight electronics. These are mostly transparent, so you can also build transparent electronics or transparent applications. This has also very strong light matter interaction, which is advantageous for the optoelectronic applications. And as this question was, if you create these heterostructures, you can also tune the properties, which results into these material on demand. Now worldwide, if you see, there are a lot of programs. Pretty much every country has got a big 2D center, and something similar we are pushing now, where there's a proposal with Government of India. But if you see worldwide investment, already in 2D materials, there's more than $1 billion investment worldwide. So now what the world has demonstrated? The world has demonstrated these flat transistors, ultra-scale transistors with 2D materials, neuromorphic computing with 2D materials, sensing with 2D materials, also solutions for heterogeneous systems like EMI, heat spreaders, peripheral technologies with 2D materials, or also cryogenic electronics, terahertz or integrated optoelectronics with 2D materials, and going forward some initial demonstrations on qubits or quantum sensing or single photon detector or sources with 2D materials. Now let's see how the 2D material push started. So in the beginning, it all started with the graphene discovery, and then a lot of work happened around graphene. People tried to demonstrate pretty much everything with graphene, right? Then came the 2D materials. The 2D TMDs were discovered, and like what people did with graphene, they also tried exploiting everything with 2D TMDs. Then there was a time when, while the explorations continued, people started realizing that what is possible and what is not possible with 2D material in terms of scalability at an industrial scale. And then industry started picking it up. So this was when the first 100 transistor 2D chip was demonstrated. And this was when the industry efforts started, and around 2020, industry has demonstrated the improved technology on a 12-inch wafer, right? With a roadmap or a projection that by 2030, the world will be able to demonstrate heterogeneous integration with 2D materials. Now, these are the timelines. If you see, 2017, the first 2D processor came out. Then IMEC demonstrated some of these things. By 20, it announced that soon we will have a 1-atom thick microprocessor, right? And a lot of industries being involved. If you see the same time, this is IRDS. So earlier days there was a roadmap document called IRTS. Now there is a document called IRDS, which basically covers everything from devices to systems, right? Devices to systems. So in 2016 there was no 2D materials, 2D transistors into the roadmap, right? 2017 this got introduced with doubts on timelines, and if you see 2020 document, it says that by 2028 the 2D transistors will be there in industry scale process, right? Now worldwide, if you see, there are a lot of new experimental fabs coming up. This is experimental pilot fab in Europe, where now they are taking designs and will can process your wafers and send you wafers back. This is a report from TSMC last year, where they demonstrated 2D nanosheet transistors, and some of these things which are not publicly available, but this is from Intel, where they were asking solution for a 2D PMOS, right? And then this is from Intel last year, where they demonstrated IEDM 2D material based transistors, right? And now this is a company which came on 2D materials last year called Paragraph, where they have started producing these 2D material based niche products. Paragraph.
So what product they are making?
In the beginning, they are making some of the sensors and all, mostly sensors. But if you see their roadmap, they said that soon we will also have electronics, right? And now all that push happened because of the possibility or the capability of 2D material to do heterogeneous integration. So what is heterogeneous integration? since you can do all these features with 2D material, you can think of building a universal process. And using that universal process, you can basically build various functionalities on the same chip, integrate them together, and make systems or basically these products which offer these heterogeneous capabilities. Right? So if so as far as the transistor or the electronic capabilities are concerned, you can scale transistor dimensions down to less than a nanometer, and we are talking about physical dimensions, not the node of the transistor. You can also build neuromorphic devices and neuromorphic systems out of these 2D materials. These 2D materials, as I said, also offer a lot of interesting properties for building these chemical bio touch sensors, right? And if you have built these chemical or bio or touch sensors, you build these arrays of these sensors, integrate that with a neuromorphic processor. You can even think of building these intelligent systems such as electronic skin or e-tongue or e-nose. Some of the e-skin are already demonstrated with 2D transistors. Similarly, you can build a lot of these interesting optoelectronic sensor, optoelectronic devices. You build these optoelectronic sensor arrays, integrate with a neuromorphic processor. You can think of building these artificial vision based systems, right? And also, since they are transparent to light, you can think of building transparent displays and many other applications of graphene which are out there. And it does not stop here. You can also build these quantum devices, qubits or quantum computing communication systems, which also further acts as an enhancer for these heterogeneously integrated systems where you have classical as well as quantum integrated all on the same chip. On top of that, you can also augment silicon nodes. So you can do certain things on silicon and certain things on top of that using 2D material, so that augmentation of silicon node is also possible. Right? So think in this way, that earlier these different applications were catered by different kind of material platforms. Now with 2D material, you can do everything pretty much using the same platform. And how do you do that? You build this kind of a Lego set, and depending on what platform you want to build, you can turn on or turn off those modules, and you get those products out of it, resulting into either classical integration or classical quantum integration. Now let's talk about the science, technology, and other challenges. So these are various science, technology, and reliability challenges that we have worked on, and I will talk a bit on some of those aspects. For example, doing high quality growth is one of the challenge. Gate oxide is a challenge. I mean, these materials don't have their intrinsic oxides, right? So doing oxide on top of it, which is important for building a gate stack, is a challenge, right? Contact is a very fundamental challenge which a lot of people have worked on. Now channels are, so making the channel intrinsic is also a challenge. For example, in experimental world, you would see papers saying that 2D materials are intrinsically n-type. Now they're not intrinsically n-type, intrinsically they are intrinsic, but they behave n-type because of sulfur defects, and these sulfur defects create donor states in the presence of oxygen and moisture. This is something which we found. We wrote a paper on that, which is also a reason for the hysteresis shown in 2D material based transistors. So how to make these transistors then passivate these defects or make it intrinsic or undo this unintentional n-type behavior, right? Then how to dope these 2D materials intentionally, how to build the process without having the PR residue sticking on it. So what happens is these 2D materials are just 1 atom thick. Now any process that you do, you will use photoresist. The photoresist, sometimes they have affinity towards surfaces, and if you don't have a proper well-defined process, the PR would stick to the 2D material, and sometimes the PR can also take out the 2D material, leading to damages, right? So how to build a process which is PR residue free. Also building a selective n-type and p-type channel for CMOS operation was a challenge. Then what we discovered, there was a time dependent channel degradation breakdown. Now this is not there in silicon. For example, silicon, if you apply a certain field, no matter for how long, as far as the field is below the breakdown, the channel will remain intact, nothing will happen, right? I'm just talking about, just take a silicon, block, apply field, nothing will happen. But in 2D material, we found that there are two critical fields. One critical field for the breakdown, avalanche, and another critical field which results into a certain phase change across the channel, right? Now, how to avoid that phase change, for which you have to dig deeper and find why there is this phase change, right? Then long-term BTI reliability and large-scale integration. This is also something that we recently looked into. So let's talk about the contacts to begin with. Now, why contacts are important? Now, there are two reasons. One is to get the maximum out of transistor in terms of drive current, and also if you want to build a transistor for higher switching performance or RF performance, if you look into the switching, the cutoff frequency of the transistor, the transconductance is there in the numerator and the resistances are there in the denominator. Now, this resistance is also contact resistance, but the transconductance is also affected by contact resistance. So if you have very high contact resistance, your FT will be less, your drive current will be less, and certainly the performance is going to be far poor than what you need, right? So this is the state of the art of the graphene. You see a lot of scatter points, right, where the performance varies because of various technological aspects. Now, as far as the quantum limit for the contact is concerned, what people do is they calculate based on the amount of charge present at one side, at the semiconductor side. On the other hand, you have the metal, and based on that, you basically calculate a particular quantum limit, how much charge exchange will happen, barrier will be formed, right? So if you look into this and plot the quantum limit, what you find is that the graphene, for example, is somewhere around 200 ohm micrometer, and TMD is somewhere around a few kilo ohm micrometer. Now keep in mind that this quantum limit assumes that the two sides are non-interacting, chemically non-interacting, right? So when you form a junction, the metal is behaving metal, semiconductor is behaving semiconductor, and at that interface there is no chemical interaction. Now this is the fundamental principle when you do this calculation. Now this is what we challenged, that if we have to break this quantum limit, can we do certain chemical interaction at this interface, right? So the question we asked was, can we break or touch the quantum limit? Now I'll first brief you about what happened in graphene, and then I'll come to the TMD part. So in graphene, like what happens with any new material, in the beginning people will try out the traditional ways and demonstrate some betterment. So it's very obvious, if I do a contact with cleaning, without cleaning, the contact without cleaning is going to be better. But still you get a APL paper or a nanoletter paper, because you are doing it for the first time. In the beginning you are demonstrating something, the world does not know how to make things happen, right? So what people tried rapid thermal annealing, showed 2x improvement in the contact. This is very obvious. Substrate passivation showed some improvement in the contact. Plasma heating, some improvement in contact. Photoresist free interfaces, some improvement in the contact, or the cleaning of that contact region. So mostly annealing or cleaning. It's very obvious that the contacts are going to be better. You land the contact metal in a better way versus in a pathetic way. Of course, where it lands better, the contacts are going to look better. But nothing was anywhere close to the quantum limits, right? Far away from the quantum limits. Now, then people started giving the classical, semi-classical picture for these contacts. For example, in case of graphene, people said that, look, at the Fermi level, the density of state is close to 0. So if you put a metal on top of it, even if there's one electron transfer, there's a huge barrier being formed because of the depletion at the graphene side, and that barrier causes this contact resistance. And people calculated that for a carrier density of 10 to the power 12 centimeters square at graphene, you are going to have a contact resistance of 160 ohm micrometer, right? Now what we did, we basically questioned this because we felt that there is a failure in Schottky barrier theory. Why there was a failure? So this will work. When this works, if you lower the temperature, what happens is that the thermionic tail goes down, and because of that the thermionic emission probability goes down, right, and therefore the contact resistance or conduction will come down, the contact resistance will appear to be higher, right. So if you lower the temperature, you measure higher resistance if there's a Schottky barrier. What we noticed that in case of graphene, when you lower the temperature, you actually get better contacts. Now, a lot of physicists have already reported, not this observation, but just to report better contact resistance, they had reported contact resistance at lower temperatures. But nobody questioned this, that why you are getting a lower contact resistance at lower temperature. When you go with this theory, you should be getting a higher contact resistance. So that was one thing we questioned, and that's when we started looking into the chemical interaction. And if you want to investigate chemical interaction, what will you do? You study the hybridization, right? So you have to get into the quantum chemistry of that interface, right? So that's when we started exploring the quantum chemistry of the interface, and we found that depending on the metal that you choose, right, and depending on the metal you choose, a particular metal would have a certain valence state, and depending on that valence state and the number of electrons present in that valence state and the energy gap from graphene, from the graphene hybridized energy state, you see some difference, some correlation in the contact resistance. So that is when we started digging deeper. But let me talk about another school of thought or other works that people did. People tried certain engineering techniques on contact, with showing improvement in contact, but without explaining why there's an improvement. So one was people demonstrated 1D contact, side contacts, showed improvement. One was increased this, made these kind of patterns in the contact area, showed improvement. Some people had shown this kind of etched region, showed improvement, but nobody explained why there are these improvements. And still the improvements, since those things were not explained, you're not designing it knowing how it works, right? You have just demonstrated, one being higher, one being lower, right? The numbers are still nowhere close to quantum limit or below quantum limit. Now this was the graphene part. Similar thing happened in 2D TMDs. So in 2D TMDs, people tried different things, but the most common aspect that people tried was, except in some cases the electrostatic doping, most common aspects was that people tried charge transfer doping, right? And there are a list of papers, here as well as here, a list of papers and a list of chemicals in which people would have dipped the transistor to demonstrate lower contact resistance. If you notice, all these papers are in these so-called high-impact journals, Nanoletters, Nature, and whatnot. And what most of these people did, so you take any of these salts, right? You make a solution, right? You will have certain ions. Because of the electronegativity difference, there will be a certain charge transfer. And when you make these, so what they do, they make the transistor, they make the contact, then you dip it, then you measure the resistance, and you show that the resistance has gone down, the problem solved, right? So what happens when you make the transistor, you have the contact and this edge with the 2D material. So these ions go and stick at the edge, and that is where basically they lower the Fermi level, or the gap between the Fermi level of semiconductor and the metal, and that's how the transport gets better. So far so good. But is that useful? That's not useful, because the moment I process the next step, say I do a gate stack or anything else, I'll do a DI water cleaning. The moment I do a next step, even if I don't do a DI water cleaning, I have to deposit a PR. The PR I have to remove, right? So there will be a DI water cleaning, right? The moment I do that next step, that salt is gone. So while I can demonstrate contact resistance being lower, the next step, the contact is gone, right? It's again back to the normal, back to that high resistance state. So while there are a lot of papers, all these papers are useless, right? Just because I cannot adopt it in an industrial scale solution. So this was the state of the art. In case of graphene, the best numbers reported were, for silicon carbide, which is the best quality graphene, as expensive as diamond, 100 ohm micrometer, and for CVD 200 ohm micrometer, but measured at 4 Kelvin, not room temperature, right? Room temperature was somewhere here, the best numbers. So we started digging the quantum chemistry, right? What we did, I mean, out of many experiments, what you see is what has worked. I'm not talking about what did not work. So in one of the experiments, we're trying to play with the overlap length, and our idea was to find if there is an optimum overlap length which gives the best contact. The thought process was that the conduction will happen from this overlap region, right? So if I increase the overlap length, let's see how much overlap is needed. But what we found, which was very interesting, that when you plot the overlap length versus the contact resistance, right? So these were all calculations, DFT and NEGF calculations in the beginning. So if you plot the resistance versus overlap length, and when you extrapolate this to 0, this does not go to infinity. And when you extract so if you extrapolate in this direction, what you get is when you have the infinite overlap length, and you extrapolate in this direction when you have 0 overlap, what you find that even in case of 0 overlap, there was 40% conduction. So the edge was contributing 40% of current compared to the overlap region. So we dig deeper into that, and what we found, when we start looking into the orbitals, and if the orbitals have changed, right, in the overlap region versus edge region, and if there is any hybridized state formed, what we found is that in the overlap region there was no bond formation. It was all van der Waals force of attraction, and it was a tunneling contact, right, or Schottky contact. And in the edge, we found that the carbon atoms, since the carbon atoms here, these carbon atoms were not completely satisfied, the hybridized state was not sp2, it was actually sp, right? We found that there was a bonding channel formed. So there was a further hybridization of carbon, and carbon metal, and that formed another hybridized state, right, which was a sp-d hybridized state, which resulted into a bonding channel and resulted into 40% conductivity or conduction from the edges. Now that gave us an idea of edge conduction and what's the role of edge in these conducting channels. Now we tested whether it works for all metals or only for select metals. So for that, you basically do this Mulliken charge calculation, which tells you how much is the charge sharing in that bonding process, right, which also tells you whether there is bonding or not. So when we tried palladium and platinum, so palladium has a 3d orbital, platinum has a 4d orbital, and the energy of 3d orbital in palladium is very close to the p orbital of 2p orbital of carbon, right? So we found that in case of palladium, there is a higher amount of charge sharing in the edge area versus the overlap area, which means there is a better bonding formed in the edge area. Whereas in case of platinum, which is a 4d orbital, so the orbital energy is much higher, far away from the 2p orbital, right? There is no difference in the charge sharing, which means that even in the edge area, platinum is forming a Schottky contact, right? So for this bonding to happen, you also need a metal which has valence 3d orbital or valence orbital with energy very close to the energy level of the 2p orbital of carbon in graphene. Now this is about the quantum chemistry of the graphene. Let me talk about something similar for TMDs, and then I'll come to the practical implementation. So in case of TMDs, so this defect or the vacancy, creation of vacancy in graphene gave us this idea that can we do something similar in TMD. So we tried many things in TMD. In the beginning we tried DFT, right? So we tried sulfur vacancies, sulfur interstitials, sulfur over sulfur, selenium over sulfur, many things, and also many metal combinations along with that. So what we found, to cut the long story short, is under certain defect and metal combinations, we found selective donor or acceptor states, right? So we found, either you can create these donor states or acceptor states depending on, what kind of defect you have and what kind of metal you choose, right? So, we tried many combinations, as I said, and we found those possibilities which basically gives you the best conduction possible and also selectivity between having either a donor state or acceptor state. Now if you have to make an n-type contact, you have to populate more electrons in conduction band, for which you need donor states. If you have to make a p-type contact, you have to populate more holes in the valence band for which you need acceptor states, right? And now we found a way by which you can selectively create either donor states or acceptor states. And the catch here was that not only the defect, but you also need a particular metal. So it's a hybridized state of the defected site, um, a certain vacancy being a certain interstitial being introduced, and a metal on top of that, right? So we call that okay, I'll talk about that later. We call that as metal induced gap states. Now let's come back to graphene. So how do we create those edge sites? So one way was we knock out carbon atoms from random places, or other way was we pattern these kind of edge sites. Now we did some more calculations to see if that affects the channel. So what we found is that while in the contact area, the density of state got significantly better around the Fermi level, which is going to help you make these contacts. But as far as the channel was concerned, the transmission probability did not, get perturbed. So that ensures that the channel will remain intact, but your contact gets better. So what we did, we basically came up with different ways, right, of creating these sites. So one was we basically used the electron beam to burn the local sites. So you can use the same lithography tool, electron beam lithography tool, and you can even program where to create these burns, right? So same lithography approach, you can just create, program where to create the burns, and this happens in the region where you are going to deposit the contact. So you deposit PR, open the contact, then again put it inside the litho stage, program where to create the burn, take it out, clean, deposit metal, anneal, done. Second was, you open this contact area, then we used either oxygen plasma or argon plasma to create these local damage sites, or we also created these patterns. So these are all lithographically patterned sites. So these are all backgated transistors, where we basically also created different variations of these, what kind of, so this is the contact area, and you see these small, patterned sites, and we played with the dimensions of these patterned sites. So what you see here is basically as you increase the plasma exposure time, you see the defect density going up, confirming that we are able to pattern and we are able to create those carbon vacancies. Now coming to the TMD, so we saw that what we had to do, we had to basically introduce these sulfur interstitials and a certain metal. So we discovered, or we developed this method where the H2S, which is also used as a precursor for growing MOS2 or WS2, we found that this breaks at the surface of MOS2 WS2 at a moderate temperature. Now when it breaks, what happens, the sulfur stays back and the hydrogen gets evaporated. So now the sulfur stays back, and then after that you can deposit metal. So sulfur goes as interstitial and the metal basically captures the sulfur, right? So even if you do some cleaning or whatever afterwards, the sulfur is there, sulfur is under the metal, right? So now what we did, we introduced sulfur as additional sulfur atoms at interstitial sites, and then we put metal on top of that, and depending on the metal that you have, chromium or nickel, we get either acceptor states or donor states, right? So we confirmed this with various techniques, Raman, XPS, to ensure that the material is intact. This is still 2D TMD, the band gap is intact, the material is intact, it's still semiconducting and so on. Okay, so before I come to the transistor characteristic, let me tell you that we had to deal with a lot of technological aspects as well, right? For example, building a gate stack, transferring the layer, ensuring that the transfer is without any crack, wrinkles, right? Patterning is intact, right? Gate stack, growing oxide was a challenge, so we built a gate stack for graphene. We'll also build gate stack for TMDs. Building these gate shapes, scaling the transistor size. There are a lot of technological aspects that we had to address, right? So which result into building a very long process, 6-7 masks. These are all those top gated transistors, RF transistors. Okay, now coming to the contact data. Now this is all hard fact, this is all experimental data, right? So what you see here, this is with oxygen plasma for exfoliated graphene measured at room temperature in air, right? Not 4 Kelvin, vacuum and all that stuff. And this is exfoliated for benchmark, and what you see as we increase the plasma exposure time, which means the defect density, right, you see an optimum. You see the contact resistance coming down to 100 ohm micrometer. Now that was for benchmark, the same we did for CVD. You see the contact resistance again coming down for 200 ohm micrometer, and also when the contact resistance is optimum, the variability is also the least. And all of this measured at 300 Kelvin in air. Now this was with argon plasma where the defect density was less, still you have an improvement in the contact resistance. Now this was the case when we had either created those, we had burned with E-beam, with COMB, or we had this COMB and RI or just COMB, and we found this optimum, and we had all these dimensional variations, right? So we got this optimum 84 ohm micrometer, right? And if you compare now for different approaches, CVD graphene, measured at room temperature, right? You see these numbers ranging in the range of 100 ohm micrometer. So what we found there is an optimum defect density needed, which results in this V-shaped characteristic as a function of defect density, right? At a lower defect density, this is mostly tunneling contact. At higher defect density, it's mostly current crowding in the overlap region, which results in poor contact, so you need an optimum defect density. When you have very high contact resistance, there's also high dependence on the gate bias, and that's also you don't want. You don't want your contact resistance to be a function of gate bias. But when we had this sub 100 ohm micrometer contact resistance, the gate bias dependence was the least. In case of when we have no contact engineering, we found that the exfoliated material, like the quality of the material, if the quality of material is better, the contact was better. But when we had the defect engineering, there was no difference between, no implications of the quality of the material, right? And when we had the optimum contact, we had the least variation, across transistors. So the data that you saw, that was measured across 40 samples. And also when you have the least contact resistance, there was no significant difference between the data at 5 Kelvin versus 300 Kelvin. Right? So this is our data from that time. 78 ohm micrometer was for exfoliated, and 84 ohm micrometer was for CVD. Now we then further wanted to investigate whether this is the fundamental limit or there is something more. So we thought that possibly there is also a phonon limit into these contact resistances. So we built this setup which would extract the IV characteristic at nanosecond timescales, right? So sub 5 nanosecond timescales, a complete RF setup. And what you see here, as you scale the time scales, going from microseconds to nanoseconds, right, and few nanoseconds, you see a significant drop in the contact resistance further, right? And this is our recent work where we not only built these vacancies in the contact area, but also introduced another layer of graphene in contact area. So it's a bilayer graphene in the contact area and monolayer in the channel, and that resulted into contact resistance in the range of around 34 ohm micrometer, 5 times below the quantum limits. So this is all, as you improve the contact, the mobility gets better, right? I'll skip some of these things. So as you scale the contact resistance, as you see, all experimental data, the mobility gets better, the transfer length goes down, the transistor performance is not a function of, or basically the mobility does not roll off as a function of channel length, right? You get to the maximum out of transistor in terms of drive current. So if you see after a certain point, the current starts saturating. So you get to the best out of what you can get out of the transistors. And the ion by I Dirac also improves. So what does it mean? So this is standard without contact engineering, and this is with contact engineering. You see such a nice gate control and this very nice Dirac point characteristic. So this was the comparison. This was the best reported number from IBM and ours with the highest quality material, hafnium oxide, gate stack, and so on silicon carbide substrate. And this is our simple process. Simple means the cheaper one, CVD graphene, silicon oxide, gate stack, all measured at room temperature, is still 20% better than the IBM's data. If you look into RF, so we are somewhere around 55 gigahertz at 250 nanometer channel lengths, and if you compare the world, except IBM, nobody has reported these kind of numbers with CVD graphene. So this was graphene. Now let's talk about TMD. So I told you how we introduced those sulfur interstitials in the contact area and then metal on top of that. Now these are very stable contacts. Do whatever you want to do on top of that, they will behave as permanent. Now here you see the improvements because of the contact engineering. So this summarizes everything. So you see the times improvement in the transconductance, off current. Improvement in off current means the drop in the off current. On current, ion by eye off, mobility, subthreshold slope, contact resistance, right? And we also demonstrated this further on CVD monolayer, and reported contact resistance in the range of 58 ohm micrometer for WS2 and 120 ohm micrometer for MOS2. Now you remember the quantum limit tells somewhere in the range of few kilo ohm micrometer, and we got in the range of 100 ohm micrometer. So this is where we are in terms of the TMD contacts, far below what best reported numbers from around the world. Now what we also did, we also demonstrated p-channel operation. So as I told you that we were able to introduce these donor and acceptor states. So depending on the metal that you choose chromium, you get acceptor states, you choose nickel, you get donor states, right? And that resulted into this kind of, so this is a NMOS characteristic and this is a PMOS characteristic with excellent off state characteristics. So NMOS behaves as NMOS, you see a positive threshold voltage, and PMOS behaves as PMOS, you see a negative threshold voltage. And this does not conduct in this direction and this does not conduct in this direction. And before the engineering, the characteristic was like this, right? So now this got significantly improved. The drive current for NMOS got better by 12 times. The leakage got suppressed, the threshold voltage is positive, and same for the PMOS. Now this was the technology part and the contact part and the p-channel operation. And so the reason this threshold voltage shift, because in this case what we did, we did this sulfur introduction across the entire channel. So wherever there were these sulfur defects, the sulfur go and sit on those defect sites, right? So it passivates the defect, it basically brings the Fermi level down to the intrinsic level in the channel, and the contact, since we are also putting metal on top of it, it introduced those donor or acceptor states depending on the metal, forming the N-type and P-type transistor, right? So the channel became intrinsic, resulting into positive or negative threshold voltage depending on the nature of the contact. Okay, so so this is some threads from the technology side. So for example, this is one work where we demonstrated that there is an unintentional fluorine doping during the reactive ion etching of TMDs. So you would typically use a fluorine chemistry for etching TMDs, but what we found that fluorine being a very small atom, even it penetrates through the PR and also goes from the side and goes and stick over TMD. And what we found is that if you don't have a control on this, precise control on this, and this is what a lot of people think that okay, put any PR thickness, any power, any fluorine RF power or plasma power, you get the patterning done. But people did not realize that the fluorine goes and sits there and then it changes the property of the material. So what we found that if you introduce fluorine, fluorine actually dopes TMD N-type. So of course that was also a discovery. While we are trying to solve etching problem, it was also a discovery that fluorine can also dope contact, and what we found that with and without fluorine there is a almost 8 times difference in the contact resistance. But of course, as a function of that optimization, we also fixed that problem. So fluorine was also sitting in the channel, which was introducing a tensile strain across the channel, affecting the mobility, which was causing drop in the current. So we fixed that problem. We boosted the drive current, and also found a way to further engineer the contacts with fluorine. This was another work where we demonstrated for the first time, came in Nature, that the TMDs, if you stress, you just apply a field, the material is going to change its phase as a function of time. So this time dependent channel degradation or phase change of the channel was reported for the first time, and we found there's a particular critical field with a strong function of the temperature, the electrostatic state of the channel, and many other things. In fact, this year in IRPS we published circuit reliability work. So we also demonstrated circuits based on 2D materials, and then we demonstrated how the circuits will degrade as a function of stress and time. Okay, so we are towards the end. Let me conclude what we learned. I talked about how 2D can enable heterogeneous integration of classical quantum systems. There are a lot of science, technology, reliability challenges, but they can be addressed. As far as the contacts are concerned, I told you that vacancy and defect engineering is the key. So you can't do a conventional doping in TMDs, but you can basically create these donor acceptor states through vacancy or defect sites. P-channel operation, you can basically introduce through vacancy engineering. We demonstrated record low contact resistance, overall performance boost of these transistors, and also a p-channel transistor demonstration. Time dependent channel degradation and breakdown can be a showstopper. This is something which is required to be addressed. So one need to come up with solutions for that. And if you address all these solutions or all these challenges, you can build a universal process for heterogeneous integrations tomorrow. Thank you. I'll take your questions.
Thank you. Question? Yes, question?
From CMOS perspective, what is the difference in the mobility of the hole and the electron on this graphene? So depending upon the mobility, we have to size the PMOS to make it compared to the NMOS device. Because in the CMOS, if you look at silicon, so we can make it twice the size to make the mobility equal. But how much would it be in this 2D
Theoretically, there is no difference. Practically, it all depends on how well you can engineer the contacts. So for example, if you see our numbers, you will see some PMOS reported in literature, but the numbers are very low. If you see our numbers, our NMOS and PMOS drive strengths are comparable for the same channel. No, you check the paper, it's almost the same. Yeah, I mean, these numbers you compare once the technological problems are addressed. The world is still trying to address some of these challenges. Once you have addressed these challenges, then you will have more refined numbers. These numbers are a strong function of many of these technological issues. Yeah, but let me also tell you, nobody cares, right? I mean, as far as it is, the size difference is not 10x. Nobody cares. The mobility got better for two reasons. A, the contacts got better, and second is you passivated the defect in the channel. So all the scattering which was there because of the defects, that got annealed, right? So the mobility in the channel got better because of that too. So if you check the paper, you would notice the mobility got better by many times. So you don't want channel to be n-type, right? You want channel to be intrinsic. So, and the defect are the scattering centers. So if you passivate the defects, you are suppressing those scattering centers. So if you're suppressing the scattering centers, you are improving the mobility, right? And also making the channel intrinsic.
Yeah. Sir, you talk about phase engineering. As we know, like MOS2, if suppose MOS2 is the channel and we use 1T octahedral, octahedral phase of MOS2 as a contact. That is feasible or
How do you convert a 2H into 1T? There are some reports, but those are not scalable.
lithium ion intercalation is also there. When we, if a bulk MOS2 is there, and if we intercalate the lithium ion, then it will be converted into a
Not scalable processes. So computations, a lot of things can be shown, but then you need to have a process. How do you do that? Right? Even for example, I had shown you that, say, suppose you introduce these sulfur interstitials, right? But if we had not discovered that method to bring those sulfur interstitials, the computations, findings from computations are of no use. On top of that, you need to build something which is scalable, right? So it has to be scalable, it has to be experimentally possible, and it should be repeatable, right? So that 1T phase conversion is something which people have talked about. Even there are other techniques, but either they are not repeatable or they are not scalable. You mean something I had shown in my slides? I don't think I talked about heterostructures.
no, if they saying that if suppose we make heterostructure, what process would you use?
Okay, heterostructure, whatever demonstrations people have done is all exfoliated, is all ad hoc. There is no industry scale process yet to build heterostructures, right? People are talking about wafer scale dry transfer and all, but whatever people have demonstrated is all pretty much exfoliated, where what you do is you exfoliate different layers separately, and then you pick, you first identify those mono layers or whatever you want to pick, and then you pick it and you stamp it elsewhere. So it's an ad hoc method. It's not an industry scalable approach, but people use it to demonstrate different kind of architectures, hoping that somebody will build a wafer scale process to create these heterostructures.
Any other question?
You are using nickel as a contact. So, sir, in MOS2 vacancy or there. So, nickel cannot be diffused in that vacancy.
Nickel? That doesn't happen. Even if it won't diffuse, it doesn't happen.
Because, sir, I am doing work on REM,
You're doing?
working on REM.
Mm-hmm.
So, in that one, they told that nickel, because nickel diffused inside the MOS2.
At what temperatures? I mean, diffusion requires a certain temperature. So diffuse at what temperature?
At room temperature, when we apply voltage,
Okay.
then nickel as a total electrode diffused
Okay, but how many vacancies? I mean, is it like a paper where you create vacancies, or you're talking about the natural vacancies which are present, which are not too many? Okay. But even if it diffuses, it does not do anything, right? It doesn't change the characteristic. So if you make a transistor with the nickel contacts without any contact engineering, you won't get any improvement in the contact. Just the diffusion of nickel at those sites won't do much, right?
Any other question? Mostly we use the CVD method or excavation. Which better method is better for the
Oh, you want to just want to do science exfoliated, but you want to build technology CVD. So we do both. We, you know, no CVD. You know, most of the materials we buy. We do exfoliated if the purpose is not technology, but if the purpose is technology, would also then demonstrate on CVD that the method works on CVD. And sometimes it's CVD which is required. For example, some of these degradation papers that you see, they're on CVD material, because we talk about, you know, role of grain boundaries and so on. So, you know, there's no point starting with exfoliated material. You have to start with the real material where the problems exist. Nowadays, you can grow on insulating substrates. So we buy wafers which are grown on insulating substrates.
I just have a question that is there one single or multi?
Single. What is grown is single, monolayer. So our work is mixed. You know, we have used exfoliated, we have used CVD. It depends on the purpose.
So if anybody wants to work on 2D material and something, how to start?
Work on a p-type contact. P-type contact is still interesting. If you can come up with a way by which you can make a universal p-type contact, that is very interesting.
So just so what is the, like, looking at 5 years, like if you want to do large scale wafer level devices, where are the major problems?
Wafer scale process exists. I mean, the industry has already started scaling up, and you know, they have demonstrated 12-inch wafer scale process. The challenges exist in still getting a single crystal high quality monolayer across full wafer, but that's basically, that will happen. I mean, it's a matter of time. You keep optimizing, it eventually happens. Once industry starts pushing it, and once you churning out wafer, it happens. Same happened in case of gallium nitride and many other areas where, you know, the material is epitaxy, and the quality improved as a function of time. So that is going to happen. I think the biggest challenge is having the high quality full wafer scale material. Other things more or less people have addressed. P-type contact is one thing. I mean, we have some solution, but I think this still need to improve. So we are also working on various other ways of making P-type contacts. Gate oxide is something which is addressed. People have addressed it. Of course, there is scope for improvement. You keep on improving gate stack. Even for silicon, high-k metal gate stack, you know, was a topic for almost 20 plus years. Hot topic for 20 plus years. So it's going to happen for 2D as well. Reliability, you know, other than the standard hot carrier, NBTI, PBTI, I think this degradation as a function of time is going to be another interesting challenge for which people need to find a solution. But I believe that as you have better quality material, lesser defects, larger grain sizes, lesser grain boundaries, this problem will also be solved. We have noticed that this is a function of grain boundary and intrinsic defects. So if you have lesser defects, lesser grain boundaries, this problem will also be, the critical field for that degradation to start will also be pushed. And as you improve the material, possibly it will get pushed towards the breakdown limits of the limit. So it's all a function of how much the world is pushing and how much is industry pushing. But if everyone is pushing, it will happen.